So in this video, I will talk about challenges in the current scenario. Almost all operational systems are using relational databases. For example, RDBMSs like Oracle. And if you think about RDBMS, they are originally designed for operational and transactional. There is something called CORD rules. There are 12 rules, and they define how an RDBMS should be. So if you want to understand what a RDBMS in a single statement, RDBMS is nothing but a file and data on files and the software which can process the data on these files in a controlled manner by applying all those 12 CORD rules. So the concept of RDBMS came into picture to implement the core business applications, and the characteristics of core business applications are both operational and transactional. So when I say operational, so it has to be in real time. And it has to be interactive. For example, if you want to debit the money from one account to another account in your bank accounts, it has to happen immediately, and that is what is called as operational. And then what is transactional? Transactional is nothing but coordinated set of coordinated operations uh, is can be termed as transaction. So in the same example where you want to transfer money from one account to another account in your bank, um, uh, if you think about it from application perspective or database perspective, it has to update multiple tables in a data model, and it has to increase the amount in one of the records in one of the tables that are in a database that is supporting the application, and it has to reduce the amount from the same table or some other table for another record, so that your both the accounts show the correct values after the transfer is done. That is called as transactional. And RDBMS are originally designed for the use cases where they are both operational and transactional. Okay, and why I am highlighting this is, if you think about non transactional systems, we will talk about a detailed example for that later. uh, you need not implement it in a RDBMS database where transactions are key, because uh, there is no alternative than the RDBMS databases. Even though most of the applications are not transactional, they are still they were using the same databases like Oracle or Informix or SQL Server or DB2, whatever is the standard database for a given enterprise. They try to use the same databases, even though applications are not transactional. Uh, the reason is there was no alternative at that time, but now we have alternatives for that. A few of these operational applications, especially if they are not transactional, you can implement them on NoSQL databases, which we will cover later. That's why I'm talking about this statement at this time. And then not linearly scalable. I already explained what is scalable, and what is linearly scalable, and what is not linearly scalable in my previous video. And now I will talk about why database is not linearly scalable. The reason is, as I am going on to whiteboard again. So as I have explained earlier, our storage server looks like this with a bunch of hard disks, and our database servers looks like this. And then they are connected with your network switch. Okay, and you have this common storage mounted onto both the database servers. Okay, so it has to go through this network layer. The storage, whenever the database server require data from the storage and that is carved out of this storage cluster, has to go to the network layer. And I just put the dashed lines to tell you that this pool of storage carved out of this storage cluster is mounted onto both the database servers. Okay, now if you try to start implementing a transactional core business application on this cluster, uh, and it will look the architecture will look like this. You have a application server here, and in application server you have something called connection pool. Okay, and let's say you have defined it as 100. So 50 connections will go to, approximately 50 connections will go to this database, and 50 connections will go to this database server, not database server. Okay, and if you understand the IO that will be done by Oracle, I am explaining this in the context of Oracle database. If you know about Oracle, how it does IO, it does IO at block level. So even though, let's say, you are trying to uh, transfer amount from my name is Durga, I have an account, and then there is another guy called Visu, and these two guys are trying to uh, do some transactions on their accounts. Okay, let's say the request the request submitted for user Durga or account holder Durga goes through this connection pool, and the request might go to this database server. Similarly, the request for account holder Visu might go through this part of connection pool to this database. But when the request goes to the database server does IO at block level. So the block size can be at least 4 kilobytes, and it can go up to 16 kilobytes or 32 kilobytes depending upon your database configuration. Let's say your database block size is 16 kilobytes. So even though you need only one record, but when the database server does the IO, it will fetch 16 kilobytes of data from an underlying table, and that is required to support the request for these account holders Durga and Visu. So as it does 16 kilobytes of IO, there is a good probability that data related to both Durga and Visu might fall on the same block in the database. So this is the block, this is the mounted storage, this is storage cluster. So this 16 kilobyte block, this is of size 16 kilobyte. There is a good probability that data related to Durga and Visu are on the same block. Okay, so let's say the first request is for Durga. So this block is already here in the memory of this database server, and while the process is going on, even though there is no relationship between Visu and Durga, when the request for Visu comes, the block is here or here. It will be either in the other database server, or it could be on the storage if the data falls under different block. So and as I mentioned earlier, there will be another network switch between the database servers it is a private network just to communicate, transfer this data between the databases, and now Visu, let's say the data required for Visu is on the same data block which is accessed by request for Durga. So it has to do a network IO and go to the other database server, and it has to fetch this uh, block from here to here to support the request for Visu. And when it can fetch and all depends upon the activity going on this one. There can be lock events, and this is all controlled by global enqueues. And concepts like these actually it can cause a lot of overhead to make it not linearly scalable when it comes to traditional databases, traditional clustered databases. So that is what not linearly scalable is. I have explained about transactions. So in this case, we are trying to update data in the same data block for both Durga and Visu, and because of the global enqueues in a clustered environment, even though it is scalable, it is not linearly scalable because it has to support the transaction. It has to move the data blocks from one database server to other database server. It can scale because it need not do the IO for storage, because a lot of data can be cached, and a private network IO between one database server and the other database server is good enough. It's a cache. We are moving data from cache of one database server to other database server, which is much faster than doing the IO. So it is scalable definitely, but it is not linearly scalable because global enqueues, and the data structures like global enqueues can be overhead where it cannot make it linearly scalable. And the other one is data integrity. So when you think about RDBMSs, you have concepts like check constraint, referential integrity constraints, and all those things, and they also make applications not linearly scalable. And then databases are very expensive, so to implement this architecture, you have to have a storage cluster, you have to have a RAID configured on this, and you have to have highly expensive backup tools at storage level, and then you have to have powerful database servers, and you have to have at least 2 network switches with fiber optics. So all these things are very expensive from the hardware side, and also to support all these activity, for example at storage level, to support fault tolerance of hard disks, you need to configure RAID, and RAID is a very expensive software which is being licensed by the storage vendors. Similarly, at database server level, if you are implementing Oracle, you have to pay hefty amount of fees for your Oracle software to Oracle Corp. So it is highly expensive. And you have predefined schema. When we say predefined schema, when you actually create a table in database, you will define column names and also column data types, whether it is integer or character type or date type and all, and also you will specify the length of the fields. So you have a predefined schema, and this predefined schema also can make it not linearly scalable. And then the one of the most important concept or challenge is that data processing do not happen where data is stored. So if you go back to this picture, let me draw this picture again. So you have storage layer, you have a bunch of hard disks in this, you have database servers, you have a network switch, Okay, and then you have another network switch for private traffic between these two, and then you have carved out a storage pool out of this storage cluster, and you mounted it on database server. Okay, now let us say let us think about what we are trying to address here. So you have storage here, you have CPUs, memory, and also you have software, which is Oracle database, everything on the database servers. CPUs and memory. Okay, so if you think about it, let's say you have a 10 GB table on this. Okay, a table called employee details for a large organization, and let's say the table size is 10 GB. It's just hypothetical. So if you want to do count, and for simplicity sake, let's say there are no indexes on the table, and you run a query called select count of one from employee details. So this is the query. So to satisfy this query, we have to fetch the data. First we have to fetch the data of the employee tables into the database server, and then you have to apply count in the database server to get the count of the records of in the table. So the table size is 10 GB and we don't have any indexes on that. So the entire 10 GB data has to be transferred over the network to one of the database server. Let's say the request go to this database server, so it has to copy the entire 10 GB data. So data has to go through the network layer into the database server memory, and then the compiled code of this query will be applied on top of that data, and you will get the count. So that's how it will work, because you have CPUs, memory, and software, everything on the database server, but the storage is elsewhere over the network. So you have to get the data from the storage through the network, through the database server. Okay, so that is what I'm referring to when I say data processing does not happen where data is stored. So data processing will not happen in storage layer at all in most of the typical RDBMS databases like Oracle. Some processing happens at database server level, as I have explained earlier, and if you do a lot of business logic implementation at the application server level, then as part of if it is a J2E application, if you have EJBs as part of your application design, and then a lot of processing can happen in application server layer, and also in web server layer, and in the end even at browser level or client level, using technologies like JavaScript, there can be some processing happening at that as well to render the page, etc. So the main important thing is data processing. Any data processing does not happen in the storage layer. Okay, at least the data has to come to database level to start the processing. So this is one of the major challenge which they try to address as part of the big data ecosystem, where data goes to code goes to data. But in most of the RDBMSs, when you actually mount the storage over the network, storage have to data has to come to the code. And if you think about it, for a select count query, if you compile the query into code, it might be very few kilobytes. So it might be feasible to push this code, 10 kilobytes of code, to the storage layer, where you have gigabytes and terabytes of data, and process and apply the code directly on that, and that is called as data locality. And most of the big data ecosystem tools support the data locality, and we will see that how it is done later. But for now, as a challenge, you need to understand that data processing does not happen where data is stored, due to which data has to come out of the storage layer into database server or application server or client or browser level to process the data. Okay, so these are the primary challenges when it comes to current architecture of current application architectures, which follows this one. Okay, so in the next scenario, we will talk more about an use case called email campaigning, and we will see how we can achieve better scalability and um, uh, uh, by moving out of the typical architecture. So this is the typical architecture in which most of the current applications are implemented. You have databases as a cluster, and you have application servers, you have the clients, and then from storage you will get data to the database, and then the processed data might go to the application server, and then it might go to the client. That is the typical architecture, and we already discussed about few of the challenges in those architecture. And now we will see in the next videos, we will see use case called email campaigning, and how we should think about alternatives for use cases like this. I hope you are enjoying the series. See you in the next video.